Hello, welcome. This is 1.1 Points, Lines, Planes, and Polygons. This is your first video and objective of Unit 1. This is going to be a little bit of a longer video, but it kind of details a lot of the building block information that we're going to be using all year long in geometry. So this would normally be a lesson that would take an entire class period. I'm going to try and go through it pretty quick, try and get this done in about 30 minutes. I recommend that you do take notes. I did attach a sheet that should be helpful if you want to print the sheet off, as well as the blank copy of the notes of the slides. That should help you out as far as a place where you can take some notes. But if you need to pause the video at any point in time, please do so, because I'm going to go through this pretty fast. So bear with me. I'm going to get through this and you'll have all the information right there for you. All right? So 1.1 Points, Lines, Planes, and Polygons. 3 undefined terms of geometry. We have point, a line, and a plane. We can pretty much make anything we want from these 3 things. First thing, a point, an exact location in space. So we have 4 points located here: point A, point B, point C, and point D. All right, we have 4 points here. Now, the way we would name a point, all right, you can either just say the actual letter. So like, if you just have the letter A, that's point A. Or we could write out point A. Okay? But there are, you will see them written both ways, either written out point A or just the actual letter to represent a point. And we could do that with any of these 4 points. A line, so now we're taking a point and now we're extending that point in both directions to have an infinite number of points. That's a line, a set of all points extending in opposite directions forever. We have 2 lines written here. The line that we have here in the middle, where we have points A, B, and C, the way we would name that is you pick any 2 points on the line. So I could say line A, B, right? And you see above that AB, I have a line with arrows. It's hard to see these arrows, they're kind of small, but on both of these lines we have drawn here, there are arrows. That's important. If you don't have arrows, then you're not drawing a line. You're drawing something else, okay? But one way of writing it is like we have here, line AB. We also could write it out, line AB, right? We also could use other 2 letters, and we don't have to go from left to right. We could say, there's line BC or line CB. All 4 of these names represent the same set of points. They're all on the same line. Okay, so any one of these 4 are correct. The other way you can write it, if you don't know any points on the line, right, then what you can do is you have this lowercase italic letter M over here on the right. Well, this line and the set of points that's on that line could be written as line M. Okay, so you can write it a few different ways. All right. Where'd it go? All right, we're back. Now, another term here, collinear. Points are collinear if and only if they're on the same line. Real quick, that IFF term there, that stands for if and only if. It was not a typo. Okay? If and only if. If and only if is kind of like an equal sign. So if you have a statement at the beginning and at the end, and if and only if in between, it basically means if one thing happens, then the other thing is guaranteed to happen. All right? So if I have points that are collinear, if It's guaranteed that they're on the same line. And you can flip-flop them too. Not all definitions in geometry allow you to flip-flop the two facts. But if they're on the same line, then we know that they are going to be collinear as well. But the way we would read this is points are collinear if and only if they're on the same line. So points A, B, and C are collinear because they're on the same line. Now, the opposite, non-collinear, that's when you have a set of points and at least one of those points is not on the same line. So points are non-collinear if and only if they are not on the same line. So I have 3 points, A, B, and C. Well, because B is not on the line, right, we have these 3 points are a set of non-collinear points. Okay? Even though A and C are on the same line, because B is not, that set of those 3 points is a non-collinear set of points. A line segment. So we have 2 line segments here. We actually have a bunch of line segments, but we're going to talk about 2 of them. A line segment consists of 2 endpoints and all the points on the line between the endpoints. So in this case, there are no arrows on these lines. Okay, we have just A and B, and the lines stop. That makes it a line segment. The way we would symbolically write this would be line segment AB. Now there's no arrows above A and B. It's just a line drawn without arrows. Okay? That represents all the points between and including A and B. All right? Now you could write it out and you could say line segment AB. All right? Sometimes you say segment AB. With these segments on the right, there's actually quite a few segments here. I'm going to use just the one in the middle, the one between points D and E. All right? We could write that 2 different ways. We could say line segment DE or line segment ED. All right? It doesn't matter what order you write the points in with lines and segments. Okay? Because in segments, they're both endpoints. In lines, they're just going through those points forever. All right? So this is how you would write the names of these line segments. Array consists of an initial point, an endpoint, and all the points on the line extending in one direction. So it is important, all right, how we write down the rays, because rays have 2 different, they're kind of a combination of the segment and the line. There's an endpoint, but it also goes forever. So when we say our names here, so for this one on the left with points, just points A and B, this is ray AB. And I have to write it this way because A is the endpoint, that is the first point in the name, and since it goes through point B, B is the second. All right? If I go over here and look at an array that starts at point C and moves to the left, right? Well, the way we would name that is ray CB or CA. I could use either one. They'd be the same ray. But C has to be the first point in the name because it's the endpoint. Right? We'll do one more over here. We'll do ray EC. I'm going to write it out. Ray EC. Same thing, even though we don't have the arrow drawn over that, because E is the endpoint, it needs to be the first letter. Opposite rays, 2 collinear rays that share the same endpoint. Well, that should be and extend in opposite directions. So we have 2 rays here, ray BC and ray BA. These are opposite rays. When we name rays, they always go from left to right. Okay? So the end point's always first, the point it goes through is always second. So it always goes from left to right. A plane, a never-ending flat surface extending in all directions forever. We actually, in algebra, we use a plane quite often, the coordinate plane with the x-axis and the y-axis, all right? In geometry, a lot of times the planes we have are just flat surfaces. We don't have coordinates. We do have points located on that plane, but we don't have as many coordinates that we work with, right? So the way that we name a plane, to name a plane, you need 3 points, and they have to be 3 non-collinear points. So I'm going to pick 3 points. I'm going to pick A, B, and D, and we're going to name it. This is plane A, B, D. All right? It doesn't matter what order I write these 3 points in. Okay? You can name it plane B, A, D. It doesn't matter. You don't have to go clockwise, counterclockwise. You just have to pick 3 points that are not on the same line. So they have to be non-collinear, right? That's one way to name a plane. The other way, this N in the bottom right corner, that isn't point N. There's no point that it's next to. It's just the letter N on the plane. It's an uppercase italic letter. Okay, that we could name this plane plane N, and that would represent all the points on that plane. Okay. Again, if I'm going too fast, pause the video, rewind it, listen to it again. If you have questions, save those questions for when we meet on Thursday. Coplanar. Points are coplanar if and only if they're in the same plane. So a lot of times we draw planes in shapes of boxes. Excuse me. So each face of a box would represent a plane, even though we're only seeing like the front, left, right, back, front, or top, bottom. Those planes do extend forever in all directions along that plane surface. But we have on the one on the left, the bottom of our box represents a plane, and there are 4 points which we can identify as being coplanar. Point N, R, K, and P. Nope. Q and P. K goes with that. The one on top. Sorry about that. All right. So those are all coplanar because they're all on the same plane. The one on the right, we actually have a box with a 5th plane that's diagonally going between the 2 edges, top left and top right. Well, the coplanar points here would be J, M, P, and Q, because they're all on the same plane. Now, just like there's collinear, we have coplanar. Well, we have non-collinear, and we have non-coplanar. Points are non-coplanar if and only if they're not in the same plane. Now here we have, let's say, our horizontal blue plane here on the left. Well, if we looked at the set of all the points shown here, we know that they would be non-coplanar because point Z and point C are not on that blue plane. Therefore, it'd be a set of non-coplanar points. Right? We can say the same thing with our box on the right. Right? If we were talking about the plane that represents the top of the box, there's 4 points on the top of the box, but if we include one of those other 4 points, okay, let's say S, well, S, U, X, W, and V are non-coplanar because S is not on that plane. Space, the set of all non-coplanar points. So basically you've got a line represents just points on a line, all right? You've got a plane which represents points that are the combination of 2 lines. That's why X and Y axis represents the coordinate plane. Well, space, now you have a third axis. You have one that goes up and down, so you have three-dimensional things. So space is all the non-coplanar points because it's all the points in all of space. All right, here's a couple rules that go along with these geometry concepts, okay? Through any 2 points, there exists exactly one line. Okay, through any 2 points, there's one line. So if I look at point A and point B, all right, there's only one line that I can draw that goes between those 2 points. All right, now we're talking about lines, straight lines. There's only one line that can go between the two. Through any 3 non-collinear points, there exists exactly one plane. This is why we can name a plane by using 3 non-collinear points. All right. Now, just like there's only one line that goes through any 2 points, if we take a third point that's non-collinear with those 2 points on the line, there's only one plane that can go through those 3 points. All right. And because of that, we can then say a plane contains at least 3 non-collinear points, and that's always going to be true. If 2 points lie in a plane, then the line containing them lies in the plane. So when we say contains, it's kind of the key word here. Contains is kind of like it intersects. So if I have 2 points in the plane, like point E and point F, then the line that has those 2 points in it will also be in the plane. And that makes sense. If I've got a flat surface and I draw a line on that flat surface, then every point on that line is in the plane. Okay? And we could say that they intersect with one another. If 2 lines intersect, then their intersection is exactly 1 point. Okay? Lines are straight. If the 2 lines do intersect, then there's only one place that they're going to intersect. Okay? If the lines were to be overlapping completely, then they'd be the same line. So that's not 2 different lines. Okay? But if you have 2 different lines that they intersect at 1 point. If a line and a plane intersect, the intersection is a point or the line. So the example we looked at a couple slides ago, we had a line that was contained in the plane. Well, the intersection is the entire line. Now this other line in our diagram, line M, you'll see that from point B up, it's solid, but from point B down, they have a dotted line till it pokes back out down here. All right? That's because this line is above the plane, and then it goes through the plane at point B. So the intersection of line M and plane C here is point B. It's just this 1 point right here. Okay? And that, we like to say that it pierces the plane. It's like an arrow passing through a sheet of paper. If 2 planes intersect, then their intersection is a line. Okay, so the example on the left, we have 2 planes. We see that they intersect, and that line of intersection, because these planes go forever in all of those flat directions, but this line would extend forever. Okay, line ST would be the intersection of those 2 planes. When we have our boxes set up, remember the planes go forever, but it looks like our intersections would be like edges. So if I took the front and the right of this box, the intersection would be this line where the front and the edges meet. Okay, so in this case, it'd be line VR would be the intersection of the front and the right plane located on that box. This one's a little bit harder to see, but if 3 planes intersect, then their intersection is a line or a point. I think it's easier to see the point because we've got, let's say, the front, the right, and the top of this box. Well, where do they all meet? At point V, right? That's the intersection point, would be just that point V. even if we were to extend all the planes to kind of overlap one another, the only point they're going to share is going to be that one point. Now the difference is if you have 3 planes and you have them all meet at one place in the middle, they would have an intersection of a line. Okay? But that's the only way planes can intersect. 3 planes can intersect at a point or a line. All right, that takes care of a lot of those building blocks things. Now we're going to move on to some of the things we can construct. All right, and that's a polygon. Now, you guys are familiar with polygons. We're going to go through this pretty quick. But a polygon is a plane figure formed by 3 or more segments called sides, such that no 2 sides with a common endpoint are collinear, and each side intersects exactly 2 other sides at one endpoint. You'll understand that definition more after we look at a few examples. But it's basically saying that it ends up being completed, so there's not going to be like 2 endpoints that just end in a polygon. They're going to go all the way around, all right? And you're never going to have a vertex that has more than 2 sides meeting at that point. So the way you name polygons, okay, the way you name polygons is you basically start at one point. I'm going to start here at A, and I'm going to work my way around the polygon. And you have to name every point basically where there's like a corner or where 2 sides meet. Okay, we call that a vertex. So this will be polygon A, B, C, D, E, F. All right? Now, I could have started anywhere, and I could have gone counterclockwise if I wanted, but you've got to continue to go in the order as you're working your way around. So I can start at E and go, let me go the other direction. E, D, C, B, A, F. You've got to use all vertices when you're naming a polygon. Okay? Now, same idea, you could have like a scripted F in there, all right? And say this is polygon F. You could do that as well. Parts of a polygon, we have sides. Looks like in this case we got 1, 2, 3, 4, 5, 6 sides. Sides are segments. Okay? They're not lines. Sides are segments because they have endpoints. A vertex. So the vertex is where 2 sides meet. So we have 1, 2, 3, 4, 5, 6. 6 sides, 6 vertices. Consecutive vertices are any 2 vertices that are next to each other. So A and B are consecutive vertices. A and F are consecutive vertices. D and E are consecutive vertices. Consecutive vertices are just as you're going around the polygon, clockwise or counterclockwise, they're the ones that are next to each other. So this is going to be, you guys should know most of these slides. And there's a lot of slides, but I'm going to go through them pretty quick. So classifying polygons, 3-sided polygon is a triangle. 4-sided, quadrilateral. 5, pentagon. And you'll notice that there's kind of the normal looking pentagon, but then the one on the right, it's still a pentagon because it's 5-sided, but it doesn't look so much like a pentagon. So, but it doesn't matter. It's just the number of sides. 6, hexagon. 7 is the one that always gives everybody problems. Heptagon. 7 sides, heptagon. 8, octagon. 9, nonagon. 10, decagon. 11 undecagon, and 12 dodecagon. Now, if we have polygons with sides greater than 12, we can just say the number of sides with the word gon afterwards. So like a 20-sided figure would be a 20-gon, okay? There are some names for some of these, but from a classifying standpoint, you can use the number and then the suffix gon. Okay. A regular polygon, that's a polygon is regular if and only if all sides are congruent and all angles are congruent. Okay? Congruent means equal to or the same. So a polygon is regular if you've got the same angles all the way around and the same side lengths. Again, a square is a really good example of one. We use squares all the time. Pretty much when you think of polygons, like a pentagon or a hexagon, in your mind, you're probably thinking of a regular pentagon or a regular hexagon. Okay, a diagonal, a line segment between any two non-consecutive vertices of a polygon. So if I want to draw the diagonals, a diagonal is not going to go from one vertex to the one next to it, adjacent to it, okay? But I can draw, there's two diagonals, 3, 4, 5. That was a pentagon and there were 5 diagonals. Well, let's see, this is a 1, 2, 3, 4, 5, 6. This is a hexagon. Let's see how many diagonals there are here. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9. I think there's only 9. When they look like this, they're a little bit harder to do. Okay, find those diagonals, but those diagonals still exist. They just you gotta, when you draw them, you can't draw them to the consecutive vertices, but to all the other vertices. Okay, so in this case, you can actually find a pattern of how many diagonals. There's no diagonals in a triangle. There's 2 in a square. We did this one. There's 5. And I think there were 9. Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. Okay. So we are going to talk about this and what the pattern will be, because there's actually a little formula that you can use to find the number of diagonals in a polygon. Okay. A convex polygon, that's a polygon. Sorry, a polygon is convex if no point from any diagonal of the polygon lies outside of the polygon. So I think one way, I'm going to draw one here. So a convex polygon is any polygon that basically continues to move without having any, so all these diagonals are going to be inside. Okay, they'll be inside. But if I had one that went like this, well, now I know right away there's a diagonal that is outside the polygon, right? Meaning that this is not convex, right? It is concave. A polygon is concave if a single point from any of its diagonals lie outside the polygon. I like to tell myself if I see 2 sides caving in towards the center of the polygon, then it's concave. Okay, if it caves in, it's concave. So if you can draw a diagonal that goes outside the polygon, it's concave. All right, we made it. So If you have any questions from this, I want you guys to write them down, have them ready for me. Thursday, we're going to talk about this lesson a little bit, and we're also going to introduce Edulastic and GeoGebra and talk about a few more of those online tools you're going to need throughout this semester. All right. Good luck to you guys, and I'll see you guys on Thursday or Friday of this week. Bye.